This bomber carries a nuclear weapon. It is a well-designed, carefully maintained, skillfully flown airplane. But airplanes, just like it, have crashed and burned. There was no nuclear explosion, no radioactive fallout. These are the facts. The Bombardier watches over controls as safe as human ingenuity can make them to prevent accidental bomb release. But nuclear weapons have been dropped inadvertently. There was no nuclear explosion, no radioactive fallout. These are the facts. And specially instrumented aircraft verify these facts in a continuing nuclear safety program that tests our nuclear weapons under controlled conditions that simulate every conceivable hazard. Vital to this nuclear safety program is Air Force Special Weapons Center at Albuquerque, New Mexico. Here, in ultra-modern laboratory buildings, work scientists in and out of uniform. They work with the incredibly complex equations of nuclear physics, which derive from Einstein's famous relationship of mass to energy. These cryptic figures, programmed into lightning-fast computers, are the theoretical base upon which these scientists, together with those of the Atomic Energy Commission, can build nuclear weapon safety. By research, design development, and laboratory test, they ensure weapons not yet built against accidental nuclear explosion. They have been doing this successfully since 1945 in safety conferences with other Defense Department agencies and the Atomic Energy Commission. In 13 years, there have been a few accidents, but not one has resulted in nuclear explosion or radioactive fallout. These are the facts. What keeps our nuclear weapons safe? To understand why there has never been an accidental nuclear explosion, you must first know how these explosions can be produced, the general principles of nuclear explosions.
Any explosion is the result of a very rapid release of a great amount of energy. Conventional explosions result from the rearrangement of whole atoms in some explosive material. For example, in TNT, the rearrangement of whole atoms of hydrogen, carbon, nitrogen, and oxygen produces explosive force. On the other hand, nuclear explosions result from the rearrangement within each atom. This may be a joining together or fusion, as in an H-bomb, or the splitting apart or fission, as in an A-bomb. At present, an H-bomb explosion starts with fission. So the splitting of the nucleus of the atom is the basic principle of nuclear weapons. All matter is composed of one or more of the 100-odd elements. Of these, the atoms of the metals uranium and plutonium can be most readily fissioned to cause nuclear explosion. These elements are mildly radioactive. They emit short-range, low-penetration alpha particles while in their unfissioned state. These alpha particles do not have the harmful effects of the longer range and stronger gamma rays, which are given off by certain elements such as radium or by the products of nuclear fission. The atoms of uranium and plutonium are among the heaviest. Heavy because the nucleus of each atom contains large numbers of the fundamental particles called protons and neutrons. When a free neutron hits this nucleus, it splits into two parts, releasing more neutrons which may go on to split other nuclei. The resulting fission products become highly radioactive, emitting the long-range and dangerous gamma rays. The split nucleus weighs less than the whole one, and this difference in weight is released in the form of energy, nuclear energy. After fission, harmful gamma radiation. Before fission, innocuous alpha radiation. To build up a nuclear energy release, the fissionable material must be of a certain size, shape, or density. Then one of the neutrons escaping from a split atomic nucleus will, in turn, split another, and a chain reaction is set up. The mass is now releasing nuclear energy, but not quickly enough to cause a nuclear explosion. This condition is called critical. If the mass is now suddenly increased, so that more neutrons are trapped each time an atomic nucleus is split, a multiplying chain reaction is maintained. Now the mass is supercritical, causing a nuclear explosion. Density of the fissionable material can be as important as mass in building up a nuclear explosion. The same sphere can be compressed so that the atoms are closer together and neutrons split more atomic nuclei, making the smaller mass critical. If compressed still more, a multiplying chain reaction sets in, causing the mass to become supercritical in a nuclear explosion. Nuclear weapons make use of both of these principles. A gun-type device can increase the mass of fissionable material to a supercritical state instantaneously. One subcritical mass is propelled forcibly into another by an ordinary powder charge. The increased mass becomes supercritical. A multiplying chain reaction builds up until the nuclear explosion. Obviously, if any mechanical device keeps these two subcritical masses apart, the weapon is nuclear safe. Applications of this fact prevent accidental nuclear explosions in gun-type weapons. Another kind of nuclear weapon is the implosion type. It compresses the fissionable material to greater density to make it supercritical. To do this, the sphere is enclosed by a shell of ordinary explosive designed to direct its explosive force inward. This effect is called implosion. The detonators attached to the explosive are connected to a complex firing device, which can fire every detonator simultaneously. When all the explosive is detonated simultaneously, the nuclear material is compressed into a supercritical mass, which results in a nuclear explosion. Implosion-type weapons are nuclear safe because only the specially designed firing device can produce the simultaneous detonation of all the ordinary explosive, a deliberate effect possible only by the precise firing mechanism. Should a single detonator be fired accidentally, whether by malfunction, crash impact, or fire, the explosive would not provide the all-around compression necessary for implosion. Instead, it might push the nuclear material out of the shell, break it into small pieces, or even burn it. This unfissioned material emits only alpha particles because no nuclear explosion has taken place. These alpha particles do not penetrate the skin. The simplest precautions can prevent their intake into the body, and the simplest cleanup measures can remove them. So you see, each type of nuclear weapon has its own safeguards against accidental nuclear explosion. These are the facts.